Have you ever heard of chemical twins? I mean, seriously, it's a real thing. You can have these molecules with the exact same list of ingredients, the same number and type of atoms, but just because those atoms are arranged a little differently, they have totally unique personalities. Today, we're going to unlock all the secrets of these fascinating compounds, which we call isomers.
And hey, welcome to the John Lilly Memory School. So glad you're here. My goal today isn't just to throw a bunch of facts at you. Nope, we're going to give you the tools and, more importantly, the memory tricks to make sure all this stuff really sticks with you for a long, long time.
All right, so here's our game plan. First, we'll cover the basics. What in the world are isomers? Then we're going to dive deep into the two main types, structural isomers and stereoisomers. And of course, we'll wrap it all up with a quick memory check just to make sure you've got it down cold. Ready? Let's do this!
Okay, first things first. What exactly is this whole phenomenon we're talking about? Let's get a super clear definition so we're all on the same page.
So, isomerism. It's this really cool idea where different compounds can share the exact same chemical formula. That means the same atoms in the same amounts. But, and this is the key, they have totally different arrangements of those atoms. It really is like having the same ingredients but a completely different recipe.
Now, isomers fall into two big categories. On one side, you've got structural isomers. This is where the actual connections between the atoms are different. Think of it like you have a box of Legos, you take the model apart, and you rebuild it in a completely different way. But on the other side, you've got stereoisomers. Here, the connections are exactly the same, but their arrangement in 3D space is different. The Lego model is built the same way, but maybe you've twisted it into a whole new shape.
Let's start with that first family, structural isomers. And I like to call them the connectors. Why? Well, because for this whole group, the difference is all about which atom is bonded to which. It's all about those fundamental connections.
Our first type of structural isomer is the ionization isomer. This is what happens when an ion, just kind of hanging out on the outside of the main complex, decides to swap places with a ligand that's on the inside. And the memory tip here? It could not be simpler. The ion, it swaps. That's it.
Check out this example. It makes it perfectly clear. In that first molecule, you see the bromide ion is right in there, bonded to the cobalt on the inside, and the sulfate ion is on the outside. But look at its isomer. They've traded places. Now the sulfate is on the inside, and the bromide is on the outside. A perfect example of an ion swap.
Okay, next up is the solvate isomer. Now this is really just a special type of ionization isomer. The twist is that the molecule doing the swapping is a solvent molecule, which, let's be honest, is almost always water. And the name kind of gives it away, right? Solvate sounds a lot like solvent. Just remember it's all about that water molecule trading places.
Now, linkage isomerism. This one is super interesting. It only happens with these special ligands called ambidentate ligands. You know, ambi means both, just like in ambidextrous. These guys have two different atoms they can use to bond to the central metal. It's like they have two different hands they can use to shake.
So take a look at this NO2 group. In the nitro complex, on one side, it's the nitrogen atom that's forming the bond, the link to the cobalt. But then in the nitrito complex, poof, the whole group has flipped over, and now an oxygen atom is making that connection. It's the same group, but a totally different link.
Our last type of structural isomer is the coordination isomer. This one is like a partner swap. It happens when you have a compound made of two complex ions, a positive one and a negative one. All that happens is the ligands from the positive complex just swap places with the ligands from the negative complex. A simple trade.
All right, let's switch gears and move on to our second main category, stereoisomers. And I like to call them the shapers. For this group, remember, the atom-to-atom connections are exactly the same. The difference is all about their 3D shape. And as you're about to see, that shape is everything when it comes to how these molecules actually work.
So just to be crystal clear, stereoisomers have the same bonds, but the atoms are just positioned differently in space. Now this category is divided into two main types you need to know, geometrical isomers and optical isomers.
Geometrical isomers are all about relative positions. You know, are the ligands neighbors, or are they on totally opposite sides of the molecule? We've got special terms for this. If they're right next to each other, we call it cis. If they're across from each other, we call it trans. And here's a great memory tip. Think of transatlantic. That helps you remember that trans means across.
In this platinum complex, you can see the difference so clearly. In the cis form, those two chloride ligands are neighbors, right? They're at a 90-degree angle to each other. But then you look at the trans form, Now they're on opposite sides of that central platinum atom, a full 180 degrees apart. Same parts, totally different layout.
Okay, now for our next type. Let's try a quick little exercise. Go ahead, hold up your hands in front of you. They look like mirror images of each other, don't they? But now, try to place one hand perfectly on top of the other so that all the fingers and thumbs line up exactly. You can't do it. And this simple idea right here is the key to understanding optical isomers.
So optical isomers are molecules that are just like your hands. They are non-superimposable mirror images of each other. You just can't stack them perfectly. These very special mirror image pairs have a fancy name. They're called enantiomers.
Okay, here's a really important tip that'll save you from a very common mistake. Ready? Tetrahedral complexes can never have geometrical isomers, ever. And you might ask why. Well, think about it. In a tetrahedron, every single position is the same distance from every other position. There is no next to or opposite. All 4 spots are totally equivalent.
Whew, we have covered a lot of ground. So now it is time to put that new knowledge to the test. Let's do a quick final check. You got this.
All right, take a close look at these two formulas. They have all the same atoms, but they're definitely arranged differently. Pay close attention to where those water molecules and chloride ions are. So, what type of isomers are they?
And the answer is solvate isomers. It's because the difference is that a water molecule, which is a solvent, right, is either inside the main complex acting as a ligand, or it's on the outside. If you got that, you've absolutely mastered it.
So I want to leave you with one final thought to really chew on. We've seen that isomers are just different arrangements of the exact same atoms, but this small difference in shape can have enormous consequences. I mean, did you know that one isomer of a drug can be a life-saving medicine, while its mirror image twin can be completely useless or even harmful? It's just a powerful reminder of how incredibly important the shape of a molecule really is.
And that is all the time we have for today. Thank you so much for joining us here at the John Louis Memory School for this explainer on chemical twins. We really hope to see you in the next one.